Good day, my angels. Hope you're all doing well. Here is our next lesson. It says this. First of all, we have a thought puzzle. Whenever an interaction occurs in a system, forces occur in equal and opposite pairs. Which of the following do not always occur in equal and opposite pairs? So which of the following don't always occur in equal and opposite pairs? Well, what I know here is Newton's third law. Newton's third law says this. Forces come in, everybody? Yes, forces come in pairs. So I know forces come in equal and opposite pairs. So let's look at the first option, impulse. Well, impulse, which is another word for change in momentum, can be calculated as force times time. Change in time, but time is always a change in, so we get lazy and stop writing the delta. Okay, well, let's see then. Since the forces are the same, opposite but same magnitude, and the time of collision has to be the same for both of them because it's the same collision for both of them, I think I can say that impulses are always equal and opposite. So since I'm looking for the one that does not always occur in equal and opposite pairs, I'll cross out impulses. What about accelerations? Well, I know forces come in pairs, so I know the force of object A on object B is negative the force of object B on object A, same magnitude. And so I also know that F equals what? MA. If the accelerations were always the same, what else would have to be the same? I think masses. So I think between collisions with identical masses, the accelerations will be the same. But if the masses aren't the same, like a big truck and a small car, you know what? The accelerations are not in pairs. That's why small vehicles often suffer so much more damage in a collision than a large vehicle. Same force, but the small vehicle will have a much greater acceleration. What about C, momentum changes? Well, momentum changes are impulses. If impulses always come in pairs, momentum changes always come in pairs. This is asking for which ones don't. So, no. Correct answer here is B. In collisions, accelerations will be different, but impulses and momentum changes, which are the same thing, will be equal, but opposite direction, one negative, one positive. We looked last day at the law of conservation of momentum. Today's lesson, lesson 5, is more C of M. Remember, C of M stands for conservation of momentum, but I tend to abbreviate. We want to talk first of all about types of collisions. There are two main types of collisions. Okay? Collisions where the objects bounce off of each other. Curling rocks are good examples of that. If you play pool or billiards, those are good examples because they don't stick together. When a baseball hits a baseball bat, the ball never sticks to the bat. Some car crashes, they stick together, but some car crashes, they bounce off of each other. A hockey body check would be a good example because generally they bounce off of each other. So there is a fancy physics word for a collision where the objects bounce off of each other, and you are going to need to know this. The fancy physics word is elastic. Collisions where the objects bounce off of each other are called elastic collisions. Now, I'm not going to ask you to define it, but you may see in a question, I say, two objects collide elastically. And what I really just told you is, hey, they bounced off of each other after the collision. Okay? The second main type of collision is where the objects stick together. A football player tackling and holding on to the ball carrier. A dart hitting a dartboard, assuming the dart doesn't fall off the dartboard. Arrow hitting a target. Some car crashes stick together. Bullet entering and sticking inside a target. not going through the target, but sticking inside the target. We have a fancy word for that. Inelastic collisions. Now, first of all, elastic and inelastic sound alike when you say them really quickly, so you'll almost always hear me say the collision was elastic or the collision was inelastic. I'll put a big pause in there because otherwise I can say that there was an elastic collision, and it's tough to set here. Did I say there was an elastic collision, or did I really quickly say there was an inelastic collision? It's tough to hear, so I'll always try and pause. How do you keep these straight? I'll tell you the same thing that I learned in high school, and this is how we've been doing it for many years. I think for elastics, I think elastic rubber band. I think rubber bounces like rubber ball or something made out of rubber. So rubber, bounce apart. Inelastic, not rubber, stick together. That's how I've remembered it for years. Elastic, rubber band, rubber ball bounces, bounce apart. Inelastic, not elastic, doesn't bounce apart. Let's look at a couple more examples. Example 1. I like example 1. I like example 1. I like example 1. Example 1 is a nice question. A car traveling 44 meters per second collides head-on with another car, different mass, traveling 22 meters per second, in the opposite directions. So I need to let one way be positive and one way be negative. I'll let this one be positive. I'll let that one be negative. You could do it the other way. I don't care. But just so that we're all doing the same work, let's do it that way. If the cars stick together on impact, what is the velocity of the collision immediately after the impact? What is the velocity of the wreckage? So, this is a collision. There's more than one object. This is a job for conservation of momentum. What's the law of conservation of momentum? The sum of all the momentum that you started with equals the sum of all the momentum that you finish with. I would give you a half mark on a test just for writing that down, because by the end of the year you've learned so much physics. I would say, you recognize that to solve this question, the approach is not a free body diagram, not DFIC, it's conservation of momentum. I'm going to call now I want to be organized but lazy. So here is how I stay organized. See where the first mass is? I'm going to put a big letter A over that. That's mass A. And I'm going to put a big letter B over that mass. That's mass B. You could write let mass A equal 1.5 times 10 to the 3rd. You can do all that if you really want to. I figure I'm going to be organized but lazy. So, before the collision, what was moving? Mass A, mass B, both, or neither? I think both were. Stuck together before the collision or separate before the collision? Separate. So I'm going to have this. The momentum of car A before the collision, initial, combined with the momentum of car B before the collision. Wham! They collide. After the collision, are they stuck together or are they separate? And which ones are moving? Okay, stick together. So it's going to be the momentum of both of them, because they're stuck together, final. Then I also know that momentum is mass times velocity. So this is going to be the mass of car A, the velocity of car A initial, and the mass of car B, the velocity of car B initial. Stuck together, so mass of A plus mass of B, V final. If they weren't stuck together, I would have a mass of A times VA final plus mass of B times VB final. There's my equation. What do they want me to find? I think they want me to find the velocity after the impact. They want me to find V final. How would I get the V final by itself? What's the bracket doing to the V final? Multiplying, you say. So I think I'm going to divide. I'm going to get this. The MA VA initial just drops down like a domino. The mass B VB initial just drops down like a domino. That's going to be divided by the mass A plus the mass of B. And actually, it equals VF, but I did the same thing that we've done so many times this year. I said I'm going to put the thing by itself over on the left because that's where I'm used to seeing it. And we're good. Now it's plug and chug. Mass A, 1.5 times 10 to the 3. Mass B, velocity A initial, 44, positive 44. Plus, by the way, conservation momentum is added plus impulse, which is final minus initial. That's where the minus sign is. Just be careful and don't put a plus where you mean a minus. Don't put a minus where you mean a plus. Mass B, 1 times 10 to the 3. Negative 22 all over 1.5 times 10 to the 3 plus 1 times 10 to the 3. Is this a fraction? Yep. Is there more than one thing on the top? Brackets around the top. Is there more than one thing on the bottom? Brackets around the bottom. Now, I'm not really quite sure what kind of an answer I'm expecting. It's possible that after the collision, car A had more momentum, and so I'll get a positive answer. It's possible that car B had more momentum, and so after the collision, I might get a negative answer. Let's find out. I think I'm going to get a positive answer. 1.5, scientific notation button 3, times 44 plus 1, scientific notation button 3, times negative 22, close off the top, divided by, open up a bracket, 1.5 times 10 to the 3 plus 1, scientific notation button, 10 to the 3. And I get positive 17.6 meters per second. So this head-on collision ended with car B getting pushed backwards and car A slowing down but still moving forwards. You know what? I labeled positive and negative in the question, so I'll just put a little positive there to let myself know I did do the direction. Let me make sure I didn't make a typo, because it's not like I've ever done that before. I think I'm right. So, hey, is this collision elastic or inelastic? Let's see. Stuck together. Inelastic doesn't bounce. Stuck together. They didn't bounce apart. Inelastic. Example 2. An 18-kilogram curling stone is traveling due east at 2.6 meters per second. It strikes at 12.5. Now, I know in real life curling stones are the same mass, but those are boring questions because then all the masses cancel. So I'm making the curling stones have different masses. Otherwise, because ice is nearly frictionless, these are really nice questions. We're actually going to be pretty accurate here. In this question, of course, this would be the velocity right after the collision, but very quickly the skidding tires would cause these vehicles to slow down, and I know that after any car accident ever, the final velocity is always 0. So this is, when I say V final, right after they collide and stick together, right after the collision. So back to our curling rock. I see east. I'm going to call east positive. And so that also makes that positive, which means I don't have to be too careful. After the collision, the first stone is moving east. Positive. What's the final velocity of the second stone? Okay. There's a collision. This is a job for conservation of momentum. The sum of all the momentum before the collision equals the sum of all the momentum after the collision. I'm going to call the 18-kilogram mass A. I'm going to call the 12-kilogram mass B. Okay. Let's see how good we are. Let's see if we can skip writing that step. Because we know momentum is mass times velocity, so let's see if I can just go to my mass times velocity equations. Before the collision, is mass A moving? Yes, it is. Is mass B moving? Yes, it is. Are they stuck together or separate? Separate. So it's going to be before the collision, I have mass A, velocity A initial, plus mass B, velocity B initial. Wham! They collide. The collision is the equal sign. After the collision, I think both are moving, because it definitely says the first stone is moving. So, and I don't think the answer is going to be 0 for the second stone. Might be, but I think they're both moving. But they're definitely not stuck together, because if they were stuck together, the answer for the question would also be 0.65, because it'd be the same as the first stone. So I'm going to have mass of A, velocity A final, plus mass of B, velocity B final. And again, remember, velocity is the vector. I'm putting the arrows to remind myself to be careful with directions, although in this question, since everything is positive, I can be a little more casual. What am I trying to find? That. How will I get that by itself? I think first I'm going to subtract the mass of A, velocity A, over to the other side. So first of all, the whole left-hand side will just drop down like a domino. And then I think I would subtract mass A, velocity A final. Don't write this next bit down. That would just leave me with mass B, VB final. And how would I get the VB final by itself? I think, well, what's the mass of B doing? Multiplying. I would divide. So instead of writing that down, I would go divided by mass B, and I'll move my thing that I'm trying to get by itself over to the left-hand side, because that's where we're used to seeing it. Again, I won't take marks off if you don't put in the vector signs. It's just a habit that I've developed to always remind myself, make sure you're paying attention to any direction changes. Let's plug and chug. I think I can fit this in on this line still. It's going to be 18, 2.6, plus 12.5 times 1.2 minus 18 times 0.65 all over 12.5. I think I need brackets around the top. $18 times 2.6 plus 12.5 times 1.2 minus 18 times 0.65, close off the top, divided by 12.5, and I get 4.008. Double check for typos. I don't see any, so I'll go 4.01. So I guess in this collision, rock A rear-ended rock B from behind, rock A slowed down, and rock B sped up. In other words, rock A passed some of its momentum to rock B, and since momentum is mass times velocity and rock B couldn't gain mass, it had to gain velocity. And again, oh, there was a direction this time, so I'll actually write the word east. I can put the @ symbol to remind myself that it's a direction. East. Is this collision elastic or inelastic? Well, here, they did not stick together. They bounced apart. Rubber bounces. Elastic band. Rubber. Elastic. The 550 gram, nice try. 0.55 kilograms. And while I'm at it, that's mass A. Now, the other thing you can do if you want, by the way, is you could use the letter C for can, or the letter S for soda, and the letter B for bullet. I usually just use A and B. It's a habit, but whatever. Do east so I see east, positive. A 12 gram, nice try, 0.012 kilograms, and that's going to be mass B. Traveling west, negative 250 meters per second. strikes the can passing through it. Afterwards, the bullet continues west at negative 55 meters per second. What's the final velocity of the can, magnitude and direction? Okay. By the way, is this collision elastic or inelastic? Well, they didn't stick together. They bounced apart, going through each other. So it's elastic. I can do that right now. Did I say collision? This is a job for the law of conservation of momentum. The total momentum you start with has to equal the total momentum you finish with. Now I know my approach. And I'm going to remember that momentum is mass times velocity. I think before the collision, I have mass A, velocity A initial, and mass B, velocity B initial. I think both the can and the bullet are moving. Wham, they collide. After the collision, the can and the bullet are still moving, but separate. So mass A, velocity A final, plus mass B, velocity B final. This wants me to find the can velocity. The can velocity is that one right there. So I guess first the whole left side would drop down like a domino. It's a very messy initial. And then I would subtract the mass of B, velocity of B final. I would subtract that over. Don't write this next bit down. That would leave me with that. I guess I'm going to divide by the mass of A. So, divided by... And that's going to be VA final. Here we go. Now I'll just be really careful with directions. And I already converted my masses, so I don't have to worry about grams or anything like that. Mass A, 0.55. Velocity A, positive 25. You know, I think I'm going to need a little bit more room. Let's do it on the next line. Here we go. Mass A, 0.55. Velocity A, positive 25, plus mass B, 0.012. Velocity of B, negative 250. And then there's a minus mass of B again, and negative 55 all over 0.55. I don't know what the answer is going to be here. It's possible the bullet went through the can and the can slowed down but kept moving east. It's also possible that when the bullet went through the can absorbed enough momentum that it reversed direction and is now going west. I don't know. It's also possible by a fluke that the momentum could have exactly canceled out and the can could have a final velocity of 0. It could have exactly come to a stop, although I doubt that. So here we go. 0.55 times 25 plus 0.012 times negative 250 minus 0.12 times negative 55. Close off the top, divided by, what did I write? Oh no, that's right. It's just 255s by a fluke. Okay, I thought I made a dumb mistake for a second there. Divided by 0.55. Is that right? 550 grams, 0.55, 25. I called east positive. 0.12 called west negative. That all looks good. I get positive, which means east. Did I make a silly typo here? Sorry, I'm looking at this answer, and I'm wondering why the soda can has somehow sped up. It shouldn't speed up. I think I've made a typo. Let me pause and figure this out. I see the typo. You were probably all screaming at me. I typed a mass wrong. Right here, it's 0.012. Ha, 0.012. I did make a typo. Oh, and I even wrote it wrong. Jeez, Dueck. 012. Well, that'll do it. And I get 20 points. That makes more sense. The can slowed down. Not by much, but it did slow down. 20.7 meters per second. Direction at, still going east because I got a positive answer. Elastic, oh, I already answered that. So there is some examples of collisions, elastic and inelastic. What's your homework? Try number 1. Number 2. 3 is good. 4 is good. Are you going to assign all of them? Most of them. 5 is good. 6 is good. 7 is good. 8 is good. We'll skip 9. 10 is good. There you go. I skipped 9 because I'm nice. Again, I'll email out the solution key on Wednesday.